Well, we're here today to hear about the work of several outstanding young scientists currently supported by the Ramsay Fellowships. The Ramsay Fellowships were established in 2008 with a significant bequest from the Ramsay family, founders of the Kiwi Polish company. And these support outstanding researchers in conducting their own independent research within the Faculty of Sciences at the University of Melbourne. These four-year fellowships aim to advance knowledge and fundamental research in the natural sciences, encourage research excellence, increase research opportunities at the University of Adelaide, and most important, provide opportunities for outstanding young Australian scientists to enhance their potential as future scientific leaders. In 2017, the family increased their support with the addition of the Fergus Ramsay Fellowship, an additional fellowship specifically supporting applied science. And we have some members of the Ramsay family on the online audience today, including Hamish and Katrina Ramsay. Katrina, it's lovely to see you again. Katrina is the current convener of the Ramsay Fellowship Committee. We acknowledge and really appreciate the significant role you've played in supporting 11 outstanding young Australian scientists to return to the University of Melbourne from all over the world. And this includes our four current fellows, Dr. James Quach, Dr. Jack Evans, Dr. Gabriel Collin, and Dr. Fiona Whelan. And you'll hear about their research today and the schools that they sit in. Now, the format of this webinar today will allow for any questions from the audience, but what we're going to be using is the chat function. And after they've given their presentation, the presenters will actually be monitoring the chat function. So don't hold back, and we expect lots of questions through the chat. So it gives me great pleasure to introduce our first fellow today, Dr. Fiona Whelan. Now, Fiona has over a decade of experience in protein engineering and structural biology research, predominantly conducted at York University, but it was in the structural biology laboratory, and obviously this is in the UK. Now, we heard about Fiona's progress yesterday, and since being awarded her fellowship, her research has focused on the evolution of bacterial small molecule binding proteins for application in biosensing. But Fiona's been taking this in many, many different directions. So I'm going to hand over to Fiona now and really look forward to hearing what you have to say.
Okay. Thank you very much, Laura. Hi, everybody who's watching online. See if I've still got my laser pointer up. That's good. How can I get rid of that bar at the top? Can everybody see that? Yeah. Yes. It'll go away eventually. So I wanted to talk to you today about some of the work that I've been developing in, as Laura said, in biosensing device development. So in order to ensure that this has an applied outcome, I've focused on industrially relevant biosensors. So biosensors essentially comprise a specific sensor which can detect any given signal. We then have a transducer that is able to transduce the signal to some sort of measurable output. And these biosensor devices are used in lots of different analytical settings, including in healthcare, poison and toxin detection, soil sample analysis, water quality, environmental monitoring, and synthetic biology and food freshness. And essentially biosensing just means that it has some sort of biological component, such as a protein or nucleic acid. So here's the summary of what I'll tell you about today. I'm talking about the industry links that I've developed over the past 2 years and the way that those have led into our biosensor design. We're focused on protein optical sensor development, and I'll tell you about that with a collaboration with chemical engineering. And the focus of today's talk is mostly on smoke taint via lignin valorization. So I'll tell you some background around that and give you a brief overview of the other projects that are running in the lab. So first to our industrial targets. Initially, I reached out to faculty who established a mentorship with Professor Jason Abel out at the Waite, and he then organised a collaboration with Professor Kerry Wilkinson, who's a wine chemist at the Waite. She has an ongoing relationship with Accolade Wines, and they're particularly interested in developing smoke taint biosensors and pesticide biosensors. Independently, I've reached out to Wine Australia, who are interested in spoilage markers and also microbial contamination or growth on both on the vines and during fermentation. I've focused a little bit of my work on lignin valorization, which has a link to smoke taint that I'll go into in a moment. And lastly, I'll mention the circular plastic economy, where we're looking at improving the biocatalysis of enzymes that are involved in breakdown of plastics. So all of these have put industry needs at the centre of this applied project to try and define biosensors relevant for industrial use. And our industry partners have requested that we make these biosensors specific. I can't see my prompts. Cheap, fast, have a good dynamic range, require minimal infrastructure and minimal expertise, and be suitable for point of use deployment. So to the approach that we've taken an approach that, given the industrial need, we think that protein optics hybrids would be the ideal biosensors for these settings. So we've identified what the target signals are based on those industrial needs, defined binding proteins that we think would be useful for sensing those target signals. Where no binding protein exists, we're using an evolution approach to design proteins to sense those signals, and then conjugated these proteins into optical devices, which we're currently testing. So I've centred on optics because we have a lot of expertise here at the University of Adelaide, and the research momentum should really help to push this project on. So I'm collaborating with Drs. Abel Santos and Cheryl Law from the School of Chemical Engineering and Advanced Photonics. And together we're developing these nanoporous anodic alumina crystals. So this is not my area of expertise. I'm really going to do my best. So they work on functionalizing the surfaces of these nanopores with APTES and then linking glutathione to that surface. Glutathione can cross-link to the amino terminus or lysine residues of our target protein biosensors. And then we flow analytes over the surface to try and monitor small molecule protein interactions. What they actually measure is this interference spectrum from white light hitting that crystal surface, and the fringing shifts in response to, as a function of the refractive index of materials that are embedded in the nanopore. They then do a fast Fourier transform to determine the effective optical thickness at the surface of that device. And you can see here a typical binding curve. So they've got glutathione associating with that surface. And then here's our protein being cross-linked to the surface. So we're currently working at the moment on detecting analyte binding. So to our first example, which is smoke taint from Accolade wines, we're looking at proteins that we've sourced from a background of lignin valorization, because they have some things in common, which I'll go into in a second. So lignin is essentially an industrial waste product. Around 2 billion tonnes is produced annually, and less than 2% of that is actually used. But if we could get them out of this polymer, these could be a valuable cheap source of aromatic compounds from which we could synthesize high value compounds. So interestingly, the combustion of lignin also releases these same molecules, which gives us a link to smoke taint. So here I've developed something that suits our expert in lignin valorization, the collaboration being with Associate Professor Stephen Bell over in the chemistry department, and also our wine chemist, Kerry Wilkinson, out at Ag Food and Wine at the Wake campus. This is a summary of Od Methylation. So having depolymerized lignin, the monolignins that are produced need to be Od methylated in order to have a direct use for synthesis of chemicals, fuels, materials, and high value flavor compounds. So this is really the rate limiting step. And for Od methylation, this just means removing a CH3 group from an oxygen atom. And this enables ring opening chemistry or modification to form our target compounds, like for flavor compound synthesis. And for softwoods, the majority of these monolignins are guaiacol based. And for hardwoods, it's formed of guaiacol and mostly syringol, so 50-50%. There is a guaiacol binding enzyme that's been identified in nature that can Od methylate guaiacol, but no syringol sensor has so far been identified. So the guaiacol binding enzyme that we're hoping to use in our biosensors is CYP2551. Now, Stephen Bell put us onto that enzyme. My very talented student, Alex Harlington, purified that for incorporation into our biosensor devices. We're hoping here to have an intermediate risk analysis phase for our biosensing devices. So essentially, after a smoke taint event, growers often aren't sure whether their grapes were subjected to any smoke taint. And in this instance, they typically proceed with harvest and fermentation without knowing whether they're at risk of having smoke-tainted wines. So in this phase, we're hoping to develop a cheap device that they could use on site to characterise the smoke taint risk in their particular grape varietals and around the vineyard without them having to spend thousands of dollars on gas chromatography mass spectrometry. So that's where these enzymes are coming in. Cytochrome P450s are a particular protein which can be bound to cofactor heme. Heme has a characteristic absorbance spectrum, and the enzyme without, critically for this purpose, the enzyme without its electron transfer components can bind to substrate, but catalysis cannot proceed. So that means it's a good binding scaffold for detecting these small molecules of interest. And substrate binding shifts the heme absorbance spectrum to shorter wavelengths based on an ion spin state shift. So here's an example. Alex has purified CYP2551, and here it is the spectrum of CYP2551 without any guaiacol, and then with the addition of guaiacol, this is a characteristic absorbance peak shift from 417 nanometers to 390 nanometers. So we know this is binding to guaiacol, and the affinity he's measured is around 0.4 micromolar, and this fits nicely with a single smoke exposure event at 7 days post onset of ripening, measured 0.7 micromolar guaiacol contamination. And the detection threshold for people tasting these samples is around 0.6 to 0.8 micromolar. So that really puts us in the right ballpark in terms of sensitivity. Alex has also made active CYP2551 and monitored Od methylation to catechol. And following peroxide treatment, he sees formation of quinones, which have this pink coloration. So we think that might give us some other options in terms of biosensing that don't necessarily involve the crystal optics devices. But here's our first prototype of an optical biosensor for guaiacol, where we've got our glutathione increase in effective optical thickness, CYP2551 being cross-linked to that surface. And then over here, you can see a modest increase in optical thickness with the application of 1 millimolar guaiacol. So we really need to improve the sensitivity of this device, and we're working on some optimization strategies around that at the moment. So as I said before, we've identified and confirmed a guaiacol binding protein, an enzyme that can Od methylate guaiacol, but none yet exists for syringol. So in comes Stephen Bell again to identify by homology and prediction another enzyme which he thought might have different specificity to this guaiacol binding enzyme. And we've cleverly called that CYP2552. So Alex went ahead and purified CYP2552, which we've determined is the first native syringol Od methylase identified. So here you can see that characteristic spectral shift from here binding to syringol in blue. This has a slightly lower binding affinity, which is about 10-fold lower affinity than what we'd be looking for to characterise in grape juice extracts. So it's possible that we may need to engineer this to improve the affinity. Alex again made active CYP2552, which he's characterised has produced 3-methoxycatechol from syringol, so it is an active Od methylase. That's good news. And then he's done peroxide treatment, which again shows, hopefully you can see that, a pink colour compound being produced, likely some type of quinone. The next challenge is, of course, glycosylated smoke taint volatile organic compounds. So VOCs don't just hang around in grapes long term. There's a temporal glycosylation event which effectively hides these compounds from typical analytics. So we're looking at developing biosensors to these glycosylated species, lest people have grape growers have an underestimate of the effect of smoke taint on their grapes. So I'm working on that at the moment. And here's an overview of some of the other projects in the lab. I think Laura mentioned that I had lots of ideas. So these are some of the ideas. We're looking at a discovery pipeline of bacterial 2-component sensors. So these are proteins that combine to small molecules. They're associated with the membrane of bacteria, and they can regulate the activity of transcription factors to bring about transcriptional responses to environmental stimuli. And Alex has used a bioinformatics approach to identify a number of 2-component sensor systems from sewage sludge. He didn't have to get the samples, so that's okay. Arctic soil samples, petroleum-associated marine bacteria, and also the human gut. And Ranjith Manaj Sabreco is a PhD candidate in my group who's looking at engineering evolving novel ligand binding specificity in these systems. Another PhD candidate in the laboratory of Keith Sherwin is Lawrence Beltrame. He's been looking at developing new one-component systems. So these are transcription factors that can directly interact with a ligand. And in this case, he set up a system where this sensor gene can be carried by a bacterial virus. So this is bacteriophage M13. He's then designed it so that the activity of this sensor regulates expression of viral protein called gene 6. And with gene 6 expression, you incur viable viral particle assembly. So that means that the viral assembly amplifies only in the presence of an active sensor, and this amplifies the numbers of viruses to go on and reinfect other bacteria, so you effectively get selection of the type of ligand binding that you have as your desired ligand specificity. So he's using that to mutate a sensor to form a specific pesticide sensor. Finally, we're looking at using the same system, but taking one step removed to improve the efficiency of enzymes associated with plastic degradation. This is a collaboration with Stephen Bell, who's interested in plastics degradation, and Professor Bronwyn Galanders, who has unique expertise in particular South Australian marine plastic contaminants, and potentially has a source for defining new peptide plastics degrading enzymes. So we're looking at defining what product would be made after the degradation of that plastic by the enzyme, incorporating that enzyme into our virus system, and then mutating the enzyme to select for enhanced production of our ligand. So we're regulating then production of gene 6 to increase viral particle synthesis, which is only resulting from a faster enzyme and greater production of this ligand. So to the acknowledgements, thank you very much to the Ramsay family for their fellowship in applied science, to Wine Australia for top-up scholarships, the Sandland Bequest, DVCR Fame Strategy Grant, Faculty of Science Research Roadmap Scheme, and also to all of the industrial partners that I mentioned, and one that I think I didn't with the AWRI. And to all of my collaborators, I covered everybody except for Andrew Howe, who's been instrumental in teaching a crystallographer how to engineer bacterial genomes. Thank you, Andrew. And to all of my students, a couple of whom I didn't have time to mention. Thank you very much. Okay, I've got the chat box, Q&A chat. I've got the chat box open. We can close the Q&A. If anybody has any questions, please type them into the chat box. Does anybody in the room have any questions? Come on.
Yeah, well, I'll start. I can stand here, can't I? With
You're
Fiona?
welcome.
Yeah.
I'm double backed.
Great. Okay. So I'm, you know, the work on the smoke taint, and what you're able to do is identify those specific components.
Mm-hmm.
How does this then, you know, how are you going to apply that to the industry? So you talked about using the grapes.
Mm-hmm.
So this is obviously discovering smoke taint before you even go ahead and, you know, produce the wine. So how are you going to design a device to do this?
So that's going to be done in consultation with chemical engineering.
Right.
So the reason that we've targeted the optical devices is that they can be made very small. So we're talking about engineering chips that'd be really small and in a tiny device that you could plug into a phone. So we want to use that for analytics in the vineyard, because a particular problem with smoke taint is that you're going to get different exposure of those grapes to smoke taint around the vineyard and across different varietals as well that can have different impacts. So we're then looking at being able to produce something that they can use at point of use, do a quick assessment that hasn't had time to accumulate those glycosylated moieties, and hopefully get an accurate measure of the smoke event. Yeah. So that's sort of the big idea. And the small ideas are really just characterising different proteins that we can integrate into those devices to establish the sensitivity that we need. Yeah. And then finally to look to do multiplexing of those analyses. So we could hopefully get a profile of guaiacol, syringol, and some other chemicals, cresols and glycosylated species to get a full profile for a particular grape varietal. But that's blue sky. So
that's terrific. We like blue sky. Okay. Now let's just have a look at the
I've got a test question. That's okay. Thank you very much to everybody for listening anyway. Shall we press on?
No, we do have time. We
Do
do
we?
have time for any other any questions.
I'm trying to get out of here.
No.
James knows.
No, I'm just checking. I don't think we do have any more questions.
I think
All
we're
right.
really interested in developing.
Yeah.
Oh, you
Yes,
can.
Jack, please.
Thank goodness.
Is the smoke taint specific to different regions? So could this research be used in other regions which are affected by smoke? So such as
Absolutely.
the California wildfire region, which
Yeah.
it's on
Yeah.
Great Wine as well.
So these are the reasons we're targeting. I guess, that's a bit to be pragmatic and cynical with the numbers of bushfires that they're getting in California, and I think South Africa and Australia as well. With climate change, this will be a really pressing concern for grape growers worldwide. So that's why if we could come into the market with a useful biosensor for point of view sensing that's cheap and fast and requires minimal expertise and really minimal kit, because I think that's the real difference between ourselves and other products on the market, is that you don't need to buy tens of thousands of dollars worth of equipment and have a devoted laboratory space, which might be suitable for large growers, but certainly won't be suitable for the long tail of very small producers. So we're hoping to target really medium to small producers.
So
with
there's no
these devices.
specificity in the smoke or the
No.
molecules that you're testing for in the air.
They will have different profiles depending on what lignin sources are around. So if they're softwoods or hardwoods, and I think people are doing a lot of research into the types of wood that's in the neighbourhood of your particular grapevines. So I'll have to get back to you on that when you start growing your vineyard.
But I think the question is, a lignin here in
Yeah.
Australia is going to be similar in lignin in California.
Yeah, and it might be that we need to tailor the sensitivities for different regions so that you might have lower
There you go.
concentrations of syringa or something in one particular type of region. So then as long as if you're multiplexing, you could make sure that you had tailored affinities throughout the device so that you could read different concentration ranges for different regions.
Well, look, thank you, Fiona. Please join me in thanking Fiona for that really excellent overview. And I think what this highlights is the impact of the research when you go across disciplines. So we really look forward, and obviously it means that we'll be drinking great wine long into the future. So thank you very much, Fiona. So it now gives me great pleasure to introduce our next fellow, Dr. James Quach. Now, prior to starting his Ramsay Fellowship, James was actually the holder of another very prestigious fellowship, the Marie Curie Fellowship at the Institute of Photonics Science in Barcelona. He was also a JSPS Fellow at the University of Tokyo. So we were very lucky to attract him back here to the University of Adelaide with the help of a Ramsay Fellowship. Now, James's research interest, as we learnt yesterday, is in all things quantum. And along with his international collaborators, James aimed to provide the first experimental demonstration of a prototype quantum battery. Now, I'm now going to hand over to James to tell us a little bit more about this, his research. And I think you'll learn it's very exciting, and James actually really achieved what he set out to do. Now, I think, can you, oh, you okay here? We just have to exit. No, don't do anything.
Okay.
Jolly good.
So let's go to the next slide.
Yeah.
Let me close this. Next slide.
Thanks, James.
Next slide. There we are. Yeah, well, thank you for that introduction, Laura. And it really is a great pleasure for me today to present again at another Ramsay Fellowship seminar. And as Laura mentioned, what I'm going to talk about today is my work on the quantum battery. So the way that I'm going to present this in the next 15 minutes is I'm going to do a gentle introduction into what a quantum battery is. And then I will talk about the work that we achieved. And then I'll conclude by briefly talking about where we go from here. So to talk about what a quantum battery is, what I need to do is define what I mean when I say battery. So a battery has three properties. It can charge energy, so it can recharge with energy, it can store energy, and it can discharge. So for the purposes of this talk, I'll mainly concentrate around charging. So let's suppose we have a single conventional battery and it stores 1 joule of energy. Now, let's say it took 1 second to charge it. That will correspond to 1 watt of charging power. Now, if we had 2 of these batteries and we charge them in series, because each battery took 1 second to charge, 2 batteries would take 2 seconds to charge, and the charging power, which is 2 joules divided by 2 seconds, would still remain at 1 watt. And we can generalize this to N batteries. So with N batteries, each one taking 1 second to charge, will take N seconds to charge in total with the same charging power. Now, charging in series isn't the fastest way to charge conventional batteries. A faster way would be to charge them in parallel. So if you had 2 batteries, each taking 1 second to charge, and you charge them in parallel, they would still take only 1 second to charge, because now the charging power is 2 watts. So that's 2 joules divided by 1 watt. And again, we can generalize this to N batteries. So with N batteries, it will still only take 1 second to charge, because now the charging power is N watts. What I want to talk about now is the quantum battery. So the quantum battery, the idea behind the quantum battery is that we want to use the laws of quantum mechanics to try and find better ways and superior ways to have quantum batteries which perform better than classical batteries can ever do. So quantum mechanics are the laws that little things like atoms and molecules obey, and they're often very counterintuitive. And one of the properties that underpins the quantum battery and quantum mechanics systems in general is the idea of quantum superposition. So classically, conventionally, batteries can either be, say, flat or charged, but they can never be in the same state, these 2 states at the same time. Whereas using the laws of quantum mechanics, a quantum battery can be both charged and empty at the same time. And that's represented there on the screen. So what this practically means is when we do a measurement on a quantum battery, which is in a superposition, if the battery is in a flat state, so each of these flash here means I made a measurement. So when the quantum battery is in a flat state, what that means is that most of the time we do a measurement, you find it in the flat state. And occasionally you'll find it in the fully charged state. But because the probability of you finding a fully charged state is so small, for all intents and purposes, you could consider the system to be flat. Now, when the quantum battery is fully charged, and I've charged it up there with a pulse of light, we do a measurement on it now, which corresponds to each one of these flashes. The quantum battery is for the most time found in the fully charged state, and occasionally you would find it in the flat state. So for all intents and purposes, you'll consider it to be fully charged. So let's suppose we have 2 of these quantum batteries now, and each of these quantum batteries individually took 1 second to charge. Now, when there's 2 batteries, you have many more states it could be in. Both batteries could be in the flat state, or one of them could be in the charged state and the other one in the flat state, or both of them are in the fully charged state. And when they're in a quantum superposition, they're in all these states at the same time. So again, when the battery is flat, what we're saying is that when we do a measurement on it, most of the times we'll find that both batteries are flat, and occasionally we'll find in one of the other states. Now let's charge it up, and you do a measurement on it. Most of the time you'll find in the fully charged state, and occasionally you'll find it in one of the other states. Now, the really surprising thing about quantum batteries is that even though each quantum battery took 1 second to charge, you charge them individually, together, to go from the empty state to the fully charged state actually takes 0.7 seconds with a corresponding charge of 2.8 seconds. So to charge 2 batteries, it takes less time than to charge 1 battery. And you can generalize this to N batteries. So with N batteries, the charging time is actually 1 on the square root of N with a corresponding charging power of N times the square root of N, where N is the number of batteries. So in principle, if you have a very large number of quantum batteries, you can charge them almost effectively instantaneously. So here are a comparison of some values. Yeah, the translation to the slides didn't happen so well, but anyway. Yeah, anyway. So here we have the first row, the values for a conventional battery. So if we had one conventional battery and it took 1 second to charge, the corresponding charging power is 1 watt. We're charging them in parallel. If we had 1 million batteries, also take 1 second to charge with a charging power of 1 megawatts. Now, if we had in comparison, if we had a quantum battery and took 1 second to charge, the charging power is 1 watt. But if we had 10 of these, it would take a fraction of a second to charge. And this time to charge decreases even further if we had 1 million of these quantum batteries with corresponding charging power of 100 megawatts. So that's the idea behind the quantum battery at a very high level. And what we wanted to do was try and prove this in the laboratory. So this was an international effort, which we led here at the University of Adelaide. It involved 5 institutions spanned over 3 countries, Australia, UK, and Italy. So here are pictures of some of the facilities that was used. And here are the researchers. So these 3 were the PhD students. They were the workhorse of this project. Brendan, Eric, and Jonathan and myself were the theoreticians, and we had Julia, David, and Cecilia as the experimentalists. So even though this was an experimental project, there was a very large theoretical component to get this to work. So this is what we did. So our quantum battery was designed using a microcavity. So a microcavity is a device which confines light to a very small region. And the way that we constructed these microcavities was to use alternating layers of alloys, which effectively becomes a mirror, a bottom mirror and a top mirror here. The technical term is called a distributed Bragg reflector, or DBR. And in between these DBRs, we had an active layer, which was made of polystyrene infused with organic semiconductor molecules, where the energy is stored. So when we shine light on it, the molecules get excited and the energy is stored. So here is an example of the actual device that we built. So the dimensions here is about 2 centimeters across and about 200 nanometers thick. So it's a very thin wafer design. So here's a zoomed in picture of what's happening inside the active layer. So initially, the molecules are in the ground state. So when we do a measurement on these things, as represented by a flash, you will find them in the flat state. But once we charge them up with photons, in our case, it was a laser, and you do a measurement on these devices, so on these molecules, you'll find them in the excited state because the energy now is stored. And this happens on a very short timescales, on the order of femtoseconds. So femtoseconds is 10 to the minus 15 seconds. So it's very quick. So we had to use very specialized equipment to see the dynamics of our quantum battery. And what we used was a system called ultra-fast transient absorption spectroscopy. So what that system is, which is represented here by this cartoon, is a system where we send light into the cavity to charge it up, and then this is called a pump pulse. Then following that, we send in a probe pulse to see where the state of the battery is. And this device here measures the reflected light from the probe pulse. And we do this thousands of times a second to characterize the energetic dynamics of the system as represented here. So across the horizontal axis is time, the vertical axis is energy, And what we see characteristically is the energy of the system gets charged and it rises. So here is actual data, actual theoretical data, I should be more precise. So on the right-hand side here, we have tau, which is the rise time it takes to charge the battery. This is the maximum capacity of the battery. And is measured in terms of the energy per molecule. And this is the charging power per molecule. And on the horizontal axis, we have N, which is the number of molecules in our system. The purple, green, and red, how much time do I have, by the way? Plenty of time? Okay, so I'll spend some time explaining. So the purple, green, and red corresponds to different operating regions of the system. Purple refers to the decay-dominated region. This is where the light escapes relatively quickly compared to the coupling strength of the molecule to the cavity. The green region refers to the strong coupling regime. This is when the light escapes at a slower rate compared to the coupling strength of the molecule to the cavity. And the red region is what we call the saturated region. This is when the molecules couple to the cavity so strongly that a phenomenon known as detuning occurs. So what you want in the ideal case is for the light to be resonant with the transition energy of the molecules. But because the molecule is coupled to the cavity so strongly, it becomes detuned from the light, laser, and so it can no longer absorb that light. And so performance degrades. On the left-hand side here is the energetic dynamics of the system. This is the energy per molecule as a function of time. And this here is simply a zoomed in version of the top around the region of interest. So what I'm going to do now is I'm going to run this simulation. Okay, maybe I'll do this. There we are. So this line here scrolls across and it shows the number of molecules, which corresponds to the dynamics on the left-hand side. So in the purple region, we have this sort of dynamics, but in the green region, we started seeing oscillations, and this is known as Rabi oscillations. And then in the red region, it becomes different dynamics altogether. So now let me go back and explain the right-hand side and its dynamics. So in the decay-dominated region, the charging time remains constant as you increase the number of molecules, but the energy capacity per molecule increases, such as the charging power, which is simply the energy divided by the time, increases per molecule. So this is known as super extensivity or super absorption. In the green region, the charging time per molecule actually decreases as you increase the number of molecules, but the storage energy remains constant, it's peaked. But again, when you look at the charging power, which is energy divided by time, it still increases, and so it still exhibits super extensive behavior with super absorption. This is what we want. But as we get into the red region, you see a degradation. This is a region we want to avoid. Ideally, we want to operate near this purple green region, because at this purple green region, we still have super extensivity in charging, but we also operate at near maximum capacity. So that was the theoretical predictions, and now we have the experimental data to back it up. So we were able to build 5 of these quantum batteries, and these are the experimental results. So this sort of noisy line, it is noisy, but it also looks more noisy because we've added error bars in there as well. And I'm superposed on top of that are the theoretical predictions. So you can see that the experimental values match the theory very well. On the right-hand side here, it's these experimental data plotted on a plot where the horizontal axis is number of photons. So here the horizontal axis is time. So what we want to see is an increase in the charging power per molecule as we increase the number of molecules, and we do see that. So we were the first team to show this, and this is the underpinning of a quantum battery. So I want to conclude this presentation by talking about where we want to go next. So what we have achieved, in a sense, is the quantum advantage of a quantum battery. But we have a device where the energy is stored. To make it useful, we want to be able to extract this energy and drive something. So this is what I want to do next. So the design that I have is to attach the microcavity, or insert a layer called a charge transport layer, which takes the photoexcited electrons and then puts it into the conduction band, which will then traverse to a storage electrode, which is represented on the right. So the storage electrode could typically be made of something like lithium magnesium oxide, and the electrons would then put this material into a reduced state. In other words, it has many electrons there. And then we also have a discharge electrode. And then between the discharge electrode and the storage electrode, you can connect your device. And here's an example which is connected to an Internet of Things. So the Internet of Things is sort of the next generation of technologies where you have devices in your house, in your office, in buildings, which are used as sensors and monitors. And I think this is a great application for the photo rechargeable quantum battery. And finally, what we need to do is then to replenish the electrons. So there'll be an interface here where we want mediators, which takes the electrons and then regenerates the photo electrode, which is this guy, at a rate which compensates for the superabsorption. So we want a system which has kinetic and thermodynamic favorability for the electrons to be transferred. And so this is the next state of my work, and I'm hoping to achieve this to build a useful device in our research. And so I'll just end the slide, in my presentation there with a summary of the slides that I've spoken about. So thank you for your time, and I guess I'll take questions now. And to do that, I guess I need to chat.
Go to chat. Well, so maybe I'll have a question, if I may,
Yes,
James.
please.
Is that you talk right at the end, around getting a device, quantum battery into everyday household items. What is in my complete ignorance, what cost would that incur? So for an item compared with batteries that we have now?
Oh, okay, so the first device will probably cost you like $50 million. But the materials that are used for these devices are not costly if you get mass produced. So I imagine, this is quite further down the steps, it would be comparable. There's nothing there, like I don't need gold or diamonds. It's a very round-of-the-mill materials which needs to be developed though.
Yeah. So what you have is a prototype with really unique properties.
Yeah.
And now you've got to kind of scale that up so it becomes a commonly used battery. And obviously that will take some more research.
Yeah, I might have been a little bit flippant. So we have done the hard bit.
Yeah.
The rest of it, I mean, in some sense, it's just engineering.
Yes.
But it's still sort of the state-of-the-art stuff which is not being developed.
Yep.
So we have to develop this.
Yeah.
But once we achieve that, then yes, and then scalability. So we are thinking as the first application is IoT, Internet of Things, because it requires only a small amount of energy.
Yeah, very good.
But if that works, then I see no reason to why we can't scale up to bigger things like mobile phones as such.
Great.
But that would be the next generation type level.
Well, I think what you've illustrated though is you've taken a concept to a device, and now you have a vision where you can take your prototype.
Exactly. So prior to our work, it was purely scribbles on a blackboard.
Yes.
And so we proved the concept, which is quite a really remarkable concept. It's the idea that if these, in my case, I use molecules. So these molecules act together collectively, quantum mechanically, they produce a better result than if they were by themselves. And not only that, the more there are, the greater the effect. So it's very, very amazing. And it's sort of why the realm of quantum tech is so interesting at the moment.
Well, and exciting, I think. And so I'll just check it. Do we have any questions? Yeah, any from the audience? Well, Fiona.
Yes.
I have a couple of questions.
Yeah.
James. So why is it that there's a maximum, do you think, number of molecules that are in there giving that enhancement? And why is that for?
Yeah, so as a technical detail, I tried to explain it a little bit there. Okay, so let me perhaps take a step back. So first we have a cavity, and a cavity has a resonant frequency. So only light of a certain frequency can get in. And these molecules, they are modeled as two-level systems. Let's call it a ground state and an energy state. We want this energy gap to be of the same frequency as the cavity and as the light mode. So when the light comes in, it couples to the cavity. But what happens is when you have more, so it couples to the molecule, we have more of these molecules, the coupling becomes so strong that they produce a quasi-particle known as a polariton. So a polariton is a quasi-quantum mechanical particle, and its energy gap changes. So the more there are, this quasi-particle becomes larger as energy gap. And when it becomes too large, it's no longer resonant with the photon. And so it can't absorb any more light. And so there's a limit to it. There are techniques and mechanisms to overcome this. For example, we could use a thing called a broadband resonator, which allows more modes of light to come in, and you would shine it with a broadband spectrum, for example. And there are other techniques as well. We obviously didn't do that because this was just a first step to show the principle that we want to show. And as we move forward, yeah, we will want to operate in those regions as well, and we will need to do these engineering type things. Right? Yes.
Yeah, Gabriel.
So is the fundamental thing that's going on here, is it a coherent interaction, the light?
So it's coherent interaction which results in interference. So I'll use a few jargon because you're a physicist. So the system is represented by a thing called a Dickey-Hamiltonian, and the eigenvalues of this Dickey-Hamiltonian produce a Dickey ladder. And what you essentially do is you climb the Dickey ladder, and the Dickey ladder, these eigenvalues are solutions which are the results of interference effect. So a little bit of background. Originally, quantum battery came from quantum information theory, and so the idea is you start off in one part of the Hilbert space, and you want to go to another part of the Hilbert space. And this part here corresponds to a flat battery. That part there corresponds to a charged battery. And the idea was that with entanglement, the trajectory is a geodesic. But without entanglement, classical thing, it's not a geodesic. It's not a shortest path. So with entanglement, you have a geodesic. But then later on, they found that you can achieve this geodesic even without entanglement, just purely from coherence and interference. And that's what we did. So we do not use any entanglement.
That's terrific. We have two sort of physicists or two physicists coming from different perspectives, but have a common interest. So, and that's again, sort of some of the beauty of interdisciplinary, I mean, I know that's within your discipline, but it shows what conversations can be had.
Yes. Yeah.
So, and keep that going. So now I'm conscious of time. So James, I'm just looking, I can't see any questions coming in from the Zoom, but thank you. I mean, that's really setting the scene for the future. And it could well be that funding from the Ramsay Foundation, this fellowship, actually generates a battery for the future. And wouldn't it be exciting to see James's work progress into a really bigger thing. So we wish you all the best with that, James.
Yeah, thank you very much. That would be a great headline.
Yes, okay, it would be a great headline. And it's very exciting. And you've also made that area of sort of the quantum, you've made that really simple today for us to understand what you've achieved with your prototype. So thank you very much and congratulations. There we are. So our final two speakers are our new fellows awarded this year. And I'm really pleased that they're here today to tell us a little bit about their planned fellowship research. So our first new fellow is Dr. Jack Evans, who actually started his Ramsay Fellowship in August of this year. Jack completed his PhD here at the University of Adelaide in 2016, and then went to Europe to join research groups in France and then Germany. And there he developed these atomistic simulations to investigate exciting materials with counterintuitive physical or chemical properties. Now, clearly I need to hand over to Jack to tell us a little bit more about this. So welcome, Jack.
Awesome. Thank you very much, Laura. And thank you for everyone on the stream and for sticking with us this afternoon. So, although Laura gave a very nice introduction to myself, I'd like to also introduce my background and kind of what brought me back to the University of Adelaide. So when I started my PhD at the University of Adelaide, the world was a much smaller place than it is right now. And during my PhD, I was really fortunate to spend some time on a research visit to Atlanta, to Georgia Tech University, where I really learned a lot about how to understand materials using some of the chemistry background that I gained during my studies at Adelaide. Then, as soon as I handed up my PhD, I got on a plane over to Europe and started my first postdoc in Paris. And I enjoyed it so much that I just kept staying in Europe and went on to my second postdoc in the city of Dresden. Now, I'm very fortunate to be awarded the Ramsay Fellowship because that brought me back to Adelaide and back to the environment that I grew up in and really allowed me to achieve these things across the world. So in my studies, I've actually been going between two very distinct fields of chemistry. Those are the realm of experimental chemistry, the usual things you think about with chemists in white coats, with glassware, mixing vials of brightly colored solutions. But also the computational aspects where we want to use computers and the simulations that computers can achieve to lead us into unexpected results or to really provide insight that we can't necessarily do in the laboratory. So when I started at the University of Adelaide, the goal was to really combine an experimental project with a computational project. But it turned out I don't really have the hands for experimental chemistry. I don't have the green thumb or whatever that is for solution chemistry. So that kind of brought me towards this more computational side. And that's what really I was able to concrete down or gain a lot more understanding during my time at Georgia Tech and then onwards at Chimie Paris Tech. I then went back to a more experimental group, but not in the lab, because I don't think anyone really lets me go into the lab anymore, but instead to work directly with experimentalists to help them direct their research towards the materials and towards chemistry, which was either more exciting, more viable, or just to tell them what this black muck on their bench could possibly be. So my research is more on the computational side, and it really spans the kind of breadth of computational chemistry, or what computational chemistry can do. So that involves some quantum simulation where we're solving Schrodinger's equation and dealing with electrons and some of the stuff that James spoke about in the last lecture. Then I also use classical simulations where we forget about electrons and forget about these quantum particles and instead treat atoms and bonds between atoms as springs. And this allows us to not just understand small molecules, but to understand very large materials and their interaction with other matter, such as gases, which you can imagine is very important when we want to understand how to trap or to separate gases. Then I try to combine this all together with some data analytics to really consider larger databases of experiments and simulations to really give us a great overview of the type of chemistry and the type of materials that are out there for different applications. So in my research at TU Dresden, my last postdoctoral position, I was really looking at porous materials. And so these are materials that have a porosity. So think of them like large sponges that can take up gases from the atmosphere. Now, the work that I was doing was really trying to push the envelope and try to find more porous materials that have been reported, or porous materials that are more porous than have been reported. And so we're looking at materials called metal organic frameworks that have increasingly large amounts of surface area. And so that surface area represents the area within a crystal of this material, for example. And so we worked on materials such as DUT49 and all the way through to DUT60 in 2018, which has experimental surface areas of greater than 7,000 meters squared per gram. And this may seem like a totally arbitrary number, but what this represents is that you can have a teaspoon of some material, and this teaspoon will have more surface area than a football pitch. So this is an amazing amount of surface area that these materials can have. And what the surface area allows you to do is to do reactions on that surface area, to attract gases to that surface area and store gases, and those type of things. But in our work, we kind of flew a little bit too close to the sun at times. It turns out you can make materials that are too porous, just the same ways that you can make buildings that are too tall. And we found that this material called DUT49 was a little bit too porous. So although it was able to behave and absorb large amounts of gas, during some certain situations, it collapsed completely and released that gas and actually showed a crystal to crystal transformation. So just under the influence of having some gas absorbed into this material, so having some amount of methane within these pores of this crystal, it was able to release the gas and really reduce its volume by up to 61% and convert again to another crystal. So a really fascinating material that we spent a lot of time trying to understand. And I think there's still some mysteries that this material is hiding from us. But one of the things that I've been really focusing on is trying to understand the structure and how this material is able to convert between these two seemingly disparate crystal forms. And so I recently was able to understand this in terms of a free energy landscape. So this is very similar to the landscapes that you would see if you look at a map of mountains and valleys. But these valleys represent low energy areas for this molecule, or for this material rather. And what we find is that this z-axis just represents energy, whereas these other axes represent the cell volume, so how dense or how less dense this material becomes, and the gas pressure that surrounds it. And we can see that there is this low density form that is favorable for all different types of pressure. But we can see that for specific gas pressure, the closed pore, or this higher density form, becomes more favorable. And it has this really unique and dynamic structural landscape that allows it to interact with these gas molecules in ways that we wouldn't really expect. And I suppose you are starting to consider, why is this important? Well, what I want to do is push these materials further, and rather than consider how they just interact with gases, but also consider how they interact with molecules to transform those molecules into something more important. So what this comes down to is catalysis. And conventional catalysis is usually done by things like zeolites or siliceous materials, which you may find in catalytic converters. They convert or put cations into your water, so you have nicer water. But they really have this type of structure here. And what is, I guess, not unique about these materials is that they're extremely static. They're relatively boring and one note. So that structure doesn't change very much regardless of the environment around it. So we can represent this like this free energy landscape, where for two different influences, we really have this one boring minima for for this material. And this is very different to nature's catalysts, like the ones that Fiona showed us in this first lecture. These catalysts can be extremely important for all types of transformations, and they are the most efficient. But so if we consider this catalyst here, it is represented by a flexible macromolecule, so made up of all different types of molecules, and which are extremely dynamic and have all these different types of forms and conformations that it's able to accommodate, so that it's able to efficiently interact with the matter and the materials around it. And so there is a step change that really needs to occur with how we generate catalysts at the moment, so that we can go more towards this vision of nature. And the reason why we want to do this is because dynamic materials have a distinct advantage over static materials. If we were to consider the interaction of some species with a surface, usually the relative energy will start at some point. As you adsorb a molecule to a surface, it will go down in energy. Then you'll do some kind of chemical reaction that will go through this transition state. And then you have a transformed molecule that's still stuck to the surface of your catalyst. Then eventually you have to go up in energy again to release the molecule into the solution or into the phase around it. So this really shows you the downside of having a static material is that you may want to strongly absorb your starting material, but then you'll also, as a downside, also strongly absorb the final material or the final molecule. Whereas if we're able to change the surface after the reaction is able to take place, we can instead increase the energy or decrease, the energy between this desorption step, which can facilitate a greater efficiency of this chemical reaction and therefore a greater efficiency of your catalytic cycle. And so this is the goal that I'm going to start to consider that these metal organic frameworks will be able to achieve because of those dynamic structures I showed before. But I guess, why do I want to use metal organic frameworks for this study? And the reason why is because of the rich diversity that these structures can have. Metal organic frameworks are sort of like the Lego building blocks of materials chemists. You can pick some kind of ligand, so any type of organic ligand you can think of, mix it with an inorganic node, and you'll have all different types of symmetries and topologies and all different types of porosity. So there is really a wealth of different structures that we can consider and apply in this application. So this is just a summary of what I hope to achieve, and I'm really looking forward to doing this project here at the University of Adelaide, and really appreciative of the support that the fellowship has provided me so far. And thank you all for your time, and for everyone at home listening as well.
Well, thank you, Jack. Now, I'm conscious that time is getting away from us a little bit. So what I might do, let's just quickly go on to chat. No, we're all right. And what I can see here is this. I love the way you talked about the computational elements and how you can use that to sort of generate new materials. And I was just thinking, if you were going to choose a material, you talked about getting back to nature. Is there anything you've got your eye on? Is there something in nature that really exemplifies what you're going to try and do here?
Well, I think this actually puts into an interesting part of this project, is that people know that proteins and nature is dynamic, but they don't actually understand the influences dynamics can have. Because the structure of many of these important proteins that drive our human body are so complex, they generally also treat them as mostly static structures. So I think this project has the possibility to not only probably suggest some materials that we can go forward to, but instead also give us insight into some of these natural processes and what influence dynamics can have in those materials too.
Terrific. Well, I think there could be conversations, Fiona. But anyway, look, thanks, Jack. It's great to have you here at the university.
Really,
and there's a lot for you to get your teeth into, and we look forward to hearing about your progress.
Definitely. Thank you.
Thank you.
Thank you, everyone.
All right. So, yes, thanks, Jack. Now it gives me great pleasure then to introduce our final speaker, our newest fellow, to the university, Dr. Gabriel Collin. Now, he's actually commenced his fellowship with us in November, but I will say he arrived in Adelaide just 2 days ago. Now, Gabriel has moved, he moved to the United States to pursue a PhD. Now, that's not true. Did you do your PhD in ANU? No, you did do it.
Undergraduate.
You're undergraduate. There you go. I'm not sticking to the script. There you go. So Gabriel actually moved to the United States to pursue his PhD in experimental particle physics at MIT. He was then employed as postdoctoral associate at the Institute for Data Systems and Society at MIT, where he developed a new statistical method for describing point sources. And these are common in astrophysical data. So I'm going to hand over to Gabriel to tell us a bit more about his planned fellowship research. But a real warm welcome to Gabriel, who's missing a cold winter in the Northern Hemisphere and obviously the start of summer here. Welcome and thank you.
Thank you for that introduction. So I'm going to talk to you about using statistical modeling for uncovering this mystery that's at the center of our galaxy in gamma rays. So gamma rays are photons that are 10,000 times more energetic than the usual visible photons that you see every day. And that means that we can get more information about some of the most exotic and violent and high energy astrophysical processes that are going on in our galaxy and beyond using these gamma rays. So what I'm showing here is a picture of the so-called night sky in gamma rays. This is a projection of the entire sky, which is commonly used in astronomy. And what you can see across the middle here is this is the plane of the galaxy. So this is in what's called galactic coordinates. And so there's a lot of gamma rays, the red area, being emitted by our galaxy. And then there's also some that are coming from outside of our galaxy as well. So if we zoom in on just the center of this image, so just this region in here, just the center of our galaxy, we can do what's called a residual plot. So what this means is we basically take everything that we understand about what's going on in the center of the galaxy and subtract that off that image so that we're just left with things we don't yet understand, right? And so you can see there's this blob here, which is red. And so there seems to be this excess of gamma rays that's coming from the center of the galaxy. The black band here is just a subtraction of taking out the entire plane, just because there's a lot of things we don't understand in there. But there's very clearly some kind of distinct blob in the center. And what's interesting about this, this blob is if we look at the energy spectrum, so this is the energy of the gamma rays measured in giga-electron volts, then we can see that there's this bump here, which is somewhat unusual for astrophysical processes, which usually have a very broad energy spectrum. And so this is suggesting there's some kind of interesting process going on here that's generating these gamma rays. So these three lines are just three different analyses of the same data set that comes from the Fermi NASA Gamma Ray Space Telescope. So this might be evidence of dark matter. These gamma rays may be coming from dark matter. So dark matter is possibly not entirely dark. It's possible that dark matter actually can annihilate with itself. And when it does this, two dark matter particles come in and they participate in a yet unknown physical process that isn't modeled by the standard model, for example, but which should produce particles that are part of the standard model. These can then in turn decay into other particles, which then can decay into gamma rays. And so if we can measure these gamma rays and determine that they might be coming from dark matter, then we can actually work backwards through this chain and figure out what's going on here, this unknown physical process, and therefore be able to develop a new theory of particle physics that can then explain what dark matter is. So this particular way of looking for dark matter is called indirect detection, as instead of directly interacting with the dark matter, we're letting it do its own thing and then seeing the indirect products coming towards us. So the reason why the center of the galaxy is such a potentially good place to look for dark matter is because dark matter is this halo of this kind of cloud that surrounds the entire galaxy and the gravity of the galaxy pulls it in, and so it concentrates at the center of the galaxy. And because the concentration is so high, the possibility of it annihilating with itself is also quite high. So this caused a potentially huge stir in the community for this reason. However, it could also be something a little more mundane in terms of astrophysics, because the center of our galaxy is quite a mysterious place, even without considering possible dark matter at the center of it. So one potential theory of what these could be is so-called millisecond pulsars, which are pulsars that have a rotational period of 10 milliseconds or less. So they're very fast spinning. And they're being predicted to potentially produce this narrow kind of energy range of gamma rays. So you can see here in the blue points here is one potential model. So it could be possible that these gamma rays are actually just being produced by these population millisecond pulsars instead of dark matter. So if we wanted to distinguish between these two hypotheses of dark matter or some kind of more mundane astrophysical process, we really need to look at the data and see what's going on there. So if it was dark matter, you would expect this kind of smoother kind of emission process where it's kind of concentrated at the center and it smoothly then has less emission toward the edges of the galaxy. Whereas if it was something like millisecond pulsars, which is population of point sources, you instead would expect to have these very bright points and very dim points instead. So you can see here, there's a whole lot of points essentially. So if we look at the data, we can potentially distinguish between these two hypotheses by doing this. So if it were due to millisecond pulsars, it'd be due to a lot of them, right? Because when we look at the data, we don't just see this, for example, and just can immediately tell, right? So any group of a lot of point sources is called a population. And so, one population of point sources is quite familiar to people. It's just the stars that are out in the night sky when you look up, right? However, when you look at the night sky, the stars are very well separated from each other. So you can see here, this kind of very intuitively reflects a mathematical modeling of points. And if we wanted to figure out the properties of this population, we could just count the number of stars as well as measure how bright they are and just create a list, which is called a catalog. However, when you have many point sources that are very close to each other, it can be difficult to distinguish between them. So this is called a crowded field. So if you had an image here that, with an ideal instrument had, say, 10 point sources that are very easy to distinguish from each other, once you move down to take into effect, like the lens optics and the point spread function of how the lens distorts the light in your telescope, and then you go down again and take into account things like quantum efficiency, as well as atmospheric scattering of light in our atmosphere. And then you go down again, you take into account digitization on a CCD, you have these discrete pixels. Suddenly you now have an image where it's actually quite difficult, and you'd be forgiven for thinking there was only, say, 5 point sources in this image instead of the actual 10, right? So this is a situation that's becoming more and more common as well in astronomy in general, as we're creating cheaper and smaller experiments, as well as experiments that look deeper into our universe, where the light is dimmer and you tend to get into these problems. So when you do have a population that's very dim and a crowded field, what you can end up with a situation is that the data you get looks very similar to what you would have if you instead had dark matter, for example. So this is a simulation I ran where I used a very large number of point sources and made them quite dim. And you can see that it is slightly different from this simulation I ran, where I essentially generated what it looked like if it was dark matter, but it is also quite close. And so in order to distinguish between these two situations, this is kind of exaggerated effect that I've shown here. But in the case of, say, the galactic center, it's much more difficult than this. You can't just look at it and see it's a little grainy, right, and use that to distinguish it. You really need to get down to the level of statistics and doing a statistical hypothesis test to tell the difference between these two situations. So if we want to create this statistical hypothesis test, what we need to do is describe what the probability of seeing a certain number of gamma rays in a certain pixel in our image is. So in the case of dark matter, which is this situation here, we would have these pixels which tend to be more moderately in intensity. So there's this kind of smooth image where it smoothly goes out towards the edge. And so if we look at a probability distribution, it's peaked at a certain particular area where this is the most probable kind of intensity you would see, and it falls off towards the edges. Whereas if you were to look at a population of point sources, instead you can see there are these pixels that are very bright and these pixels that are very dark. And actually the probability distribution looks entirely different. Instead, you have a very high probability of having dark pixels down here, and then a very high probability of having very light pixels or highly intense pixels. But then this area in the center, which did have a large peak here, is now very flat and near zero. So actually there's this pretty significant difference in the statistical distributions we can then use to figure out whether something is due to dark matter or not. So there are two current approaches to constructing these probability distributions, one of which is called parametric. And the idea behind this parametric approach is you describe the entire population of sources and not individual sources inside of it. So you talk about the total number of sources in the population, you talk about the total amount of flux that's being generated by the population, and these kinds of things. And this is a much more computationally tractable way of doing this kind of analysis, but it also requires a lot of assumptions that can be fragile, especially if you're dealing in something like astrophysics, where there's a lot of things that are not all that well understood, right? And so these assumptions can be dangerous. So the parametric approach has been previously applied to this problem of the excess of gamma rays at the galactic center under the name of non-Personian template fitting. And it came out with a result that was not consistent with dark matter. But in the last few years, I've shown that this approach is actually flawed in certain cases. And I've developed a more consistent method, just called compound Poisson generator statistics. And that's currently in review and should be published soon. There's also another method called non-parametric statistics. And so in this case, you describe the location of every potential source in the distribution and try and estimate all of them. And so because of that, it's much less reliant on assumptions. But as you can imagine, this is much more computationally intensive. So there is a leading approach for this called probabilistic cataloging. It has actually never been applied to the galactic center excess problem. And part of that reason is because of this computationally expensive aspect to it. So even though these two approaches can seem somewhat like in difference to each other, they're not totally mutually exclusive, because what we can do is create one statistical model that's a mixture of these two. So my plan is to do exactly that. And the idea is that most of our sources in our population will follow our assumptions. And so we can handle them by this much more computationally cheaper parametric method. However, there will be some remaining outliers which don't follow our assumptions, but they should only be a small fraction of our sources. And so we can actually use the parametric method to pick those up and make sure they don't bias our parametric method. So this would then create a more robust and more generally applicable method for answering this gamma ray excess problem, but also other problems in astronomy and astrophysics as well. I've previously worked on the IceCube experiment, which was a neutrino telescope at the South Pole, and I did a point source analysis on that. And so this could be then taken back to apply to looking at neutrino statistics, as well as in X-ray astronomy, whereas this is a picture on the right-hand side of the center of our galaxy in X-rays, for example. And not only in astrophysics, but there's also potential applications in other areas of science as well, for example, like fluorescence microscopy. Thank you.
That's terrific. Thanks, Gabriel. So let's see if we've got anyone on. Shall I just check? I'll check the chat. There we are. James, would you like to jump in with a question?
I've got two questions. So as I understand it, so your work is to differentiate between extended sources and multiple point sources.
Yeah.
Just seems to me a little bit speculative then to go and say that this is evidence, no matter how weak, of dark matter, because as you said, we have hypothetical particles whose process we don't even know. How can we be even remotely sure that it results in either an extended source or a distributed point source?
Yeah, so if we were to find definitive evidence or very strong evidence that there was a point source population, we could rule out the dark matter hypothesis.
Can we rule it out when we don't even know the process? How can we rule it out?
Because the dark matter hypothesis is specifically a particle that doesn't interact with other particles or itself, at least not very commonly, like only very rarely, if at all, right? And that means it can't clump together into like objects like stars, for example. You can't have dark matter stars. You have to have this extended halo. So if these gamma rays are coming from, well, do fit the point source hypothesis strongly, that means they are coming from these like compact objects, right? And the current dark matter hypothesis just cannot produce compact objects. So dark matter particle hypothesis, I should say. Obviously, there are other theories of dark that could explain the things that do fit kind of like the whole dark matter regime, like massive compact halo objects, for example, or say 30 solar mass black holes are another example, right? Those are compact objects. But here I'm specifically talking about the particular dark matter hypothesis.
Okay.
Yeah.
James, actually, what I'll have to do, I'm just conscious of time, and because you're here in the room, what I might do is get you to ask your next question to Gabriel after the webinar. But what I will say is that clearly this sort of research, very fundamental, but really pushing the boundaries of knowledge. And I quite like the fact that you've got your dark matter and your astrophysics, and I'll be interesting to see how they play off against one another. But can I thank you very much for really trying to explain, what we see at night and applying some really fundamental sort of thought-provoking concepts that we wish you all the best in unraveling in your time here as a Ramsay Fellow. So thanks so much. Now you two can go and have a little chat. And what I'm going to do is to complete the webinar by thanking all of our fellows today: Fiona, James, Jack, Gabriel. You are a credit to yourselves, your discipline, but also the Ramsay Fellowships. I'd also like to sincerely thank again the Ramsay family for your very generous and ongoing support for these fantastic young scientists. And I'd also like to take the opportunity to thank all of those of you who have joined us today online. You weren't so forthcoming with questions, but I hope you've really enjoyed the afternoon, and it's been an absolute pleasure having you with us as well. So thank you very much, everybody, and enjoy the rest of your afternoon.
Thanks.
Thank you. So there's a bit of quantum metrology where we use super